All right, looks like we have mostly everyone here, so I guess we'll just get started. Uh, Good afternoon, everyone. Welcome back to yet another class. Remember last time we talked about artificial neural networks and how they can solve a lot of really interesting problems. We talk about how they're constructed, how they're tested, some of the cool insights into how they probably work, and we finished up with a lab. So remember at the end of the last class, I was having some issues with the neural network. I've now updated the API. You can find it on the master sheet. It should be working properly now. So you can go check out the API and the homework will be based on that. Um, so when you get a chance, feel free to do that. The homework I think is due sometime this week. I'm not sure when it is, but everything should be good. Now, today we're going to be talking about something a little bit more interesting, which are convolutional neural networks. As the name might suggest, they are very closely related to regular neural networks, but there is a special operation that they carry out, which is, as the name suggests, convolution, that allows us to do some pretty cool things. So let's dive right in. Um, Before we get started, actually, I just wanted to bring up maybe a motivating example. So remember yesterday we talked about neural networks having this structure, right? You got a bunch of nodes that can carry in information. These are usually numbers. So this might be like 1, 2, 3. And it goes through all of these weights that we found using this algorithm called backpropagation that uses gradient descent to find the optimal configuration of the weights so that the error is somehow a little bit lower than when we started. So you put in these numbers and then you get out an output. Say that eventually we get all of these feeding into one neuron, and this neuron tells us the probability that these three numbers, perhaps like maybe they're an arithmetic progression. Like let's say we built a network to determine that, whether a series of numbers is an arithmetic progression. So that's cool. But we reach a challenge when we start thinking about how we want to extend this to images. Does anyone have any thoughts on maybe how we would, maybe the most naive way of trying to apply a neural network to an image? Like say you were trying to classify an image of a cat and dog, and you were trying to tell the difference between the two. How might you do that? Any suggestions? Just feel free to
Shape
unmute.
or facial features.
Oh, sorry, can you say that again?
Shape.
Shake, as in
Shape.
like,
How?
okay, shape. Yeah, so there are these very distinctive features of cats and dogs, right? Cats, they look quite different from dogs. Maybe dogs have larger noses. They the coats of fur are perhaps different colors. The shape of the head is definitely very different. Their ears look very, very different. So Kevin brings up a really good point. Maybe we want to look at some of the features. This is exactly what we were talking about last time, where you need to select the correct features for the job. So imagine perhaps we have X1 here is, and it's going to be a little bit hard to quantify, but let's say the X1 here is the fur color. Maybe that's one of the features that we could put in here, and maybe it's just some number between 0 and 255. Um, and we actually probably need three of these, three of the 0 to 255s, because we can have an RGB value. So this actually produces three neurons of input. So maybe we have fur color. Um, and then perhaps we have another neuron that says, the ear shape. This also seems like a pretty reasonable feature to be using because, cat's ears might look like this, and a dog ear might look very flappy, a lot larger. I'm very bad at drawing, but this is the general idea. So perhaps we could one hot these, meaning that, if it's 0, it's like very pointy, and if it's 1, it's on the range from 0 to 1. If it's 0, it's pointy, and if it's 1, it's sort of curvy and large, et cetera, right? You guys get the point. There are all these different things that we could use to collectively use to determine whether something is a cat or a dog. So this is a really, really good idea. So there comes sort of a challenge here, right? Because you have all of these features. It's not always entirely clear which ones are the right ones to be using. Like, who says that you can't look at the uh, the uh, the shape of the tail or something like that. There are an infinite number of features that you could derive from this image, and it's not totally always clear which ones are the correct ones. Like Kevin might say that fur color is important, and I might disagree. I might think that eye color is more important or something like that. And because neural networks take in a finite set of inputs, we can't choose everything. So we've got to pick and choose and pick the right ones. So this is a really, really good idea that actually ties in very closely to how convolutional neural networks actually work. But I wanted to ask if anyone has an even more simple idea. And a hint for this would be, think about how images are represented. Does anyone know how images are represented on our cell phones or in data?
Exos.
Yeah, they're pixels, right? So what if we were super low tech? We just took every single pixel in an image, say that we had this image here and it's a 3x3. So we have a 3x3 image and we simply flattened it. What this means is that you take this and you put it in the first place, the second place, the third place, the fourth place, fifth, 6, 7, 8, 9. And so in this neural network here, you would basically, your input layer would look like x1, x2, all the way down to x9. And you simply put all of these pixel values in these certain locations. So x3 goes here all the way down to x9, which comes here. So you put all these pixel values into the neural network. And then of course you've got some more hidden layers here. And then you've got an output. That also is a valid way of doing things, right? Because pixels, they they always appear in the same location, and perhaps we can build a model to do this. Does anyone have any objection to this idea? Like, do you see any problems with such a construction, or do you think it's perfectly good? If you think it's good, put a thumbs up as a reaction. If you think there are some issues with it, let me know what they are or what you think they are. So it seems like we have no responses, which I think makes sense because this is a little bit of a more tricky question. But just imagine this, right? You have two images and you want them to output the same thing because they both contain cats. Imagine that this is our cat here. So you have image A, which clearly should be a cat. And then you have image B, and the cat is down here in the corner. These are both images of cats. And in fact, let me make a stronger claim that this is cat X and this is also cat X. So they're the exact same cat. But unfortunately, if we were to take all of these pixels and flatten the image and put them in sequentially like this into our neural network, this would yield a very, very different representation in the input between these two images, even though they're the exact same cat, but they're just shifted around. So this is a problem called translational invariance. And to be more precise, invariance. And to be more precise, this isn't a problem, this is a desired property of our model, which means that if you take something that you're trying to classify like a dog or a cat, and you move it across the image, you shouldn't really get a wholly different representation. It should be quite similar, or in fact, we want it to be the same, because objects and images, they're all spatially located very closely to each other. Like pixels, they don't vary very much.
A question.
Objects, yeah,
Okay.
Go ahead.
What the output look like?
The output here is very simple. It's just like, you can either implement this as a single neuron outputting a number between 0 and 1, where 0 is cat and 1 is dog, or you can have two neurons that say there's a cat and a dog.
Okay. Yeah.
Yeah, but eventually we get some kind of internal representation, and my claim is that if you do something like this, where you just stack all of these pixels and flatten them, you'll get very different inputs, at least for these two things, even though they're literally the same thing. So this is a problem that we want to address. So I know I've talked about a lot on this slide, and not a lot of it is written down. So let me just recap. So first of all, Kevin presented a really nice idea where you just, as a human, you go into the picture and you look for some features that might distinguish cats and dogs, like fur color, ear shape, and then you simply just feed these into a neural network. That's a very valid way of doing things. And in fact, This is how people did it until maybe like the 2000s or the 2010s when deep learning started to come. People manually designed these features and they wrote extractors to find these features. Another valid way of doing this is just simply just brute forcing it. It's not really brute force. It's just a really dumb idea, a very simple idea. Just take all the pixels, and because pixels are numerical values, you just throw them into the neural network and see what happens. But we've identified problems with both of these approaches, right? The first approach, it is not extensible at all because a lot of the times it's hard to figure out what features are the correct features to be using. And of course, you're going to need a lot of human labor to actually design the filters that can extract these features. That's not a trivial task. So this is hard. It's just a lot of work. And sometimes the humans might not even find the best solution. And then the problem with simply feeding things into the neural network is that it's kind of dumb. You know, you're trying to use a tool for something that's not really designed for the task at hand. You're just feeding it in. There's no sequential. There is a sequential order here, but there's nothing exploiting the fact that images are not just random alignments of pixels. Objects are actually very structurally aligned in images. You know, a cat's ear is not simply just going to show up in the middle of the corner right here if the cat is right here. It's going to show up on the top of the cat's head. So there's like the spatial locality. There's this property that we want called translational invariance. There's even another one that we'll talk about later that we want, which is rotational invariance. So if you have a cat that's rotated like this, you might not want it to be classified as something different. You want it to be classified as something as the same because it's the same cat. So translational and rotational invariance are all problems with this just very naive pixel flattening representation that we need to address. So hopefully this provides a little bit of motivation and a little bit of background for why we need a better solution. And that's what we'll be talking about now. So I sort of talked about this already, but I think it's nice to just have these on a slide so that we can just go through them. The big problem here is that the domain knowledge about images is not incorporated to our neural network because it's simply just an unordered set of pixels. And when we throw them in, there's no idea, there's no notion of spatial locality, that a cat is going to be in the same region as its ear and as its nose. They're not just going to be in random locations across the image, and et cetera, et cetera. We want translational, rotational invariance. All of these problems are not incorporated to the neural network, and we want to be able to do that. So what are the properties of an image that make it very different from other pieces of data? Well, first of all, topology of pixels. I don't actually know specifically what the creators of these slides were trying to go for with this, but I think a general idea is that in images, you generally don't see very, very high contrast colors next to each other unless there's an edge. If you think about somebody's face, right, there is a very distinct sort of gradient from maybe from a darker shade because there's a shadow on somebody's face to a lighter shade because they're out of the shadow, or things like this. Like apart from edges, the pixels are not very random. They're very, very structured because, you know, objects are typically uniformly colored unless you're just taking a picture of some noise. That would be an exception. So pixels, they're all spatially co-located with each other. Again, the ear pixel will never appear very far from the eye pixel. Translational invariance, we talked about this, which is that if you have a cat, it doesn't matter where it shows up in the image, it's still a cat. We have to deal with things like lighting and contrast. So if you take a picture of the same cat, but in different lighting, your pixel values are going to be very, very different, right? They might be a lot closer to black if you take it in very low light, and it'll probably be close to white if you take it in super, super high lighting with super, super high contrast or something like that. So that's a problem. I would say that the knowledge of the human visual system is not a big deal here. But another thing is that there are edges and shapes in images. Remember, because if you have an image of a person, clearly the person's head is not going to blend into the background. There's an edge here that you need to take advantage of when you do classification. And then also something that I didn't really talk about was scale invariance. If you have a cat that looks like this, what if it looks like this? You just move your camera a little bit closer. If it's the same cat, then you should get a similar representation. So these are all problems that we need to address because images are very structured in specific ways, and we want to take advantage of that. So let's go ahead and talk about what exactly we do to fix this. So this is precisely what Kevin was talking about earlier. So you've got like these features, right? And these features are able to distinguish a cat. You might say that a cat, obviously it's got two eyes. They've got a certain relation to each other. Maybe they're next to each other and they're a specific shape. They've got a specific pupil color or pupil sort of shape. Maybe sometimes it's more oval than it is circular. You got eyes, how their eyes look. You've got fur, you know, what their fur looks like, what the color is, what the texture is. There are all of these features that you might want to design code to intercept. Because if you can design code to intercept these features, then you can feed them into a neural network and be like, yeah, so we've got all of these features and they uniquely identify this object. And based on that, you should be able to tell that this is a cat and clearly not a dog. So there's this problem, right? You've got all these features that make sense to the human eye, but humans are not always the smartest things, right? Sometimes we overlook things, we don't see obvious features that we should be using and we don't actually choose them. What if we could use a computer to build up these features, right? And this is the idea. You got features need to be built up, and the whole idea is we want to do this computationally. How do we do this? And so that's where the idea of a convolutional neural network comes in. So let's look at what this convolutional neural network looks like. This is the general structure. Don't worry if a lot of this looks a little bit abstract and confusing. We're going to dive into the details in a moment. But here you can see that it looks a little bit like a regular neural network. You have an input. It has a certain pixel value, 32 by 32. This should set off alarm bells in your head because 32 by 32 is very, very low resolution. But let's just play with this number for now. We can increase the resolution of our neural nets in a second. But you got an input, and there are all these things called convolutions. These are what I will explain later. These are the things that extract the features that Kevin was talking about earlier. But the catch is you don't actually need to design these convolutions. They're actually learned through backpropagation. And so these convolutions, intuitively, if we were trying to classify, I'm guessing handwritten letters here, so like A, B, C, D, E, these convolutions would be looking for things like, are there curved lines? For example, in an E, you don't have curved lines. You've got straight, 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 straight. But in a D, you've got one curved line and one straight line. So these convolutions are these mathematical operations that can extract such features from your input. And it does this a bunch of different times. You can see it does it once here and then does it again. And in fact, this can occur many, many times. In many popular models, there are 150, like on the order of 100 such iterations of convolutions. You do it once, twice, blah, 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 all the way to 100. And each time you're extracting new and new features, more and more abstract features. And sometimes it gets to the point where you don't know what the heck it's looking at, but it's figuring out something that minimizes the error, so you're happy with it. And eventually, at the very end, you get a set of features here. This is just a bunch of numbers. This is a bunch of numbers. Like right now, I can't really tell how many there are. It looks like there are 120. So this is just literally an array of 120 values. So x1, x2, x3, ... x120. These are what we call the final features. This is not official terminology. It's just what I like to call it. These are the final features that come out of your convolutions. And these features, you don't necessarily know what they mean, but what you do know is that they provide a representation of the original image. And what we hope is that these features encode something useful such that when we apply a regular neural network, this is just a dense neural network, the one that we saw yesterday, where every node is connected to the other nodes. Once you apply a dense neural network on this set of features, you can get the correct classification out. So if you think about this, this is basically equivalent to what Kevin said, where you have these features that might identify whether something is a cat or a dog, or whether letters A, B, C, D, E, except you're not the one finding the features. The computer will learn how to find these features. So hopefully this makes sense. Feel free to drop in questions in the chat if you have any of them.
So the C5 layer, you have 120 features. Is that a features of previous features?
Yeah, exactly. There's sort of like this recursive relationship here because these are actually the features of 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 the features. You repeat this 100 and maybe like 100 times. Features of the image. So every time.
How do they look like? Is any way we can describe that? Because it's highly abstract. It's like a very high level abstraction. I know, I can imagine, but I don't know how they look like.
Yeah, this is a good question, and it's in fact an active area of research. A lot of people don't know what's happening inside these models, and you're absolutely right. You have these features. Maybe the first convolution is more straightforward because you're simply applying a feature on the original input. But after you do this 100 times, all of the relationships, the interdependencies get entangled, and it's hard to figure out what exactly the model is thinking. Except for the fact that sometimes there are these cool interpretability tricks that people like to use so that they can figure out what the model is looking at when it makes its decision. For example, if you had an image of a cat right here, if you applied this cool trick, it's called grad cam, like gradient camera. It'll actually put a heat map around the cat, and it'll be like, this is where I got my information from. So you can visualize these filters. In fact, we will do this in a moment. We can take a look at the filters that are coming out. But unfortunately, they are so abstract that humans cannot decipher them, or at least reliably. So we sort of have to trust that the neural network is doing its job. And as you can tell, this is becoming a trend in machine learning. You have to trust the model to do its job, and sometimes we can't trust it. So that's why a lot of people are doing research to figure out how we can understand what these models are doing and whether we can control them or not.
Yeah,
all right.
Interesting. Yeah, thank you.
All right, cool. So in this model, you all already understand this part of the model, right? We already covered this yesterday. This is a fully connected network, or in other words, an artificial neural network, or whatever you want to call it. But there are these components, in particular convolutions and subsampling, that we don't know about. And these, in fact, are the components that help us extract the features that Kevin was talking about at the beginning. So let's go ahead and talk about what convolutions are. Convolutions are an operator. So, well, like, first of all, I think we should define convolution. Convolution is an operator on an image. What this means is that you take in an image, say a picture of a cat, and you apply an operator. So let's just say a conv is defined by this little thing. It's like a star with a circle in it. And you operate it with some certain thing. We'll just call this a variable x. And when you convolve these two things, you get another output and you get another image. So based on what this x is, you will get a different output. And we will see what exactly this does and why it's so powerful. So let's just define what this little x thing is. This x is called a kernel. And this is in fact the title of this slide. This is a kernel. So a kernel is basically a grid of numbers. You can think of it as a grid of numbers. That's exactly what it is. So let's say that our kernel is 3 by 3, and it's just got a bunch of random values, right? We could initialize it to 1, 2, 9, 6, 4, 1, 2, 3, 5. It doesn't matter what it is. It's literally just a grid of numbers. And what you do with this kernel is you take it, and by performing this operation, which is called a convolution, you take this kernel and you basically slap it on top of this. You slap it on top of this image. You got this kernel. You slap it on top of the image, and you move it around. You move it around in a very specific way, and you do a bunch of multiplications, and out comes a new image that's a result of multiplying this thing with this thing and moving it around. So I realize that what I'm saying is very, very vague, because I want to use a specific example to explain what are the operations that are transforming these two entities into the output entity. But this is actually not special to machine learning. This was developed way, way before machine learning became a hot topic. this is just like, it's a very, very useful tool, this idea of a convolution by using a kernel on an image that has very, very important applications in signal and image processing. We won't talk about that right now, but you should just know that traditionally people have used these filters for very cool things. Like if you've ever imagined how people, if you've ever wondered how blur works, if you ever take an image and you go to Adobe Photoshop and you apply a blur on it, this is actually how it's done. You convolve the image, original image, with a filter and it'll blur everything. You can also do sharpening with a filter. You convolve an image with a filter, and that's actually what happens when you go onto your iPhone and you hit edit and you think that the image is a little bit soft, a little bit blurry. If you click sharpen, it does a convolution of that image with a filter, and it outputs a little bit of a sharper image. So there are all these very cool things that people have done with these filters, but the catch is that people design all of these filters. All of these filters are hand designed. And what I mean by hand designed is people have designed the equations that define how these filters work. But the cool thing in convolutional neural networks is we don't really care what they are. We're going to ask our algorithm, which is the exact same algorithm we used last time, gradient descent, backpropagation, to figure out what these filters are. So during the training process, we'll be messing with these weights to make sure that our loss decreases. Okay, so now that we know the general idea behind a kernel is some set of numbers where you slap it on top of an image and you move it around and you get an output. What exactly is going on here and why is this important? Let's try to explain that. So first of all, let's try to examine the math behind the kernel, like how it operates. It's actually quite simple and it's defined by this equation. But I think this equation is a little bit harder to read than just simply doing an example, so let's do that. A kernel, to apply it to an image, because these kernels, this kernel and the image are the same size, we only have to give one output. But the whole idea is very simple. You take this kernel, and for every location, you multiply it by whatever is in the same location of the input. So 3 times -1 would be -3, right? 0 times 2 is 0. We ignore that. 1 times 1 is 1. This is -2. And I'll just keep writing. This is +6. This is -1. And this is +1. So basically what happens is you take the dot product. If you know what a dot product is, this should remind you of a dot product. You just go through it for every location, you multiply the 2 values that are at that location for both the input and the kernel, and then you add them up. So what this should turn out to is these ones cancel. This becomes a 4, this becomes a -2, this should equal 2. So your output should be a 2. And the significance of this is that if we do something, okay, well, yeah, this is a much more pretty representation of what I just said. You take this thing, you multiply it with the kernel, and so it's sort of like slapping, like I said earlier, slapping the kernel on top of the image. You just slap it on there, and then you perform the element-wise multiplication. And this is the formula that I just wrote out, and turns out that I can do basic arithmetic. The answer is indeed 2. So that's the cool thing. Well, that's how kernels work. It's not quite cool yet because this kernel looks fairly arbitrary. Like it's not doing anything that interesting. It's just, you might be wondering, why exactly do we need these kernels? Well, kernels can be very powerful if you design them correctly. Let's look at an example of something that actually is interesting. So this kernel, I mean, these 3 are all kernels. These kernels all do very specific things, and we will explore the intuition for why they work. This is what we call a vertical line detector. So whenever you have a vertical line in your image and you convolve it with this kernel, so if you have an image and you do a convolution of that image with this kernel, you will get a bunch of activations that are super, super high where there is a vertical line in the image. So, say that we have a cat, in our image, like right here. The curvy part of the cat will probably not get picked up by this vertical line detector, but the more vertical parts, for example, maybe the pointy ears, these will get picked up by your vertical line detector, and they will produce a super high activation in that area. So if you do the convolution, you might see something like super high activations in these areas, and then maybe some activations where, the lines are approximately vertical. And so this is what you would get out of this image. What is the significance of this? Well, see that in the original image, you just have the original image. This is just the object. But when you actually do the convolution, you remove all of the stuff that you don't care about, and you've selected out whatever you wanted to select out. In this case, we wanted to select out vertical lines. And this is just a map of all locations with the target thing, whatever it is, a target representation. So if you look at the kernel itself, you might realize that it sort of makes sense. It's got -1s on the sides and 1s in the middle. So intuitively, this might look like a vertical line detector to you. There's also a horizontal line detector. There's a corner detector and all sorts of different things. So to make this, to really nail this point home, that kernels are very useful for, taking out features from images. Let's do an example. So imagine that you have an input, right? This input is a bunch of values, 1, 2, 1, 3, 3, 3, 1, 1, 1. So, and now let's try to visualize what this might look like, right? And I'll try to shade this in as best as I can. So the 1 would get a little bit of shading, 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 a little bit. This one gets a little bit more shading, and then the 3 is very highly shaded. Let's just say this. And let's shade in the 2 a little bit more. What you can see here is that there's a very clear vertical line in this image, right? This is the vertical line. This is the axis of the line. And there's not really any horizontal structure here because all these horizontal things are all different. They're all different pixel values, and it's not really that interesting. And the goal here is to design filters that can take out vertical and horizontal line detectors. So let's see what the activations are when you apply both of these filters onto this image. So you have a vertical line detector here. And this is basically what we saw earlier, except I bumped up the weights to 2 instead of 1. It doesn't make a huge difference. Operationally, they're the same. But now, if we apply this and we do the operation that we talked about earlier, which is taking the dot product with this detector and the input, if you do the math out, you'll get a super, super high activation, a 13. And, the way that you would interpret this is there is a vertical line in this image. And then just as a sanity check, if we did a horizontal line detection on this image, we would get a 2, which is significantly, significantly lower than 13. And it tells you that indeed, this convolution, these kernels are effectively trying to pick out these features. And when there aren't these features, you won't have anything there. So yeah, that is pretty much it. Now, I have a question for you all. Why do you think, and this is a sort of like, it's not a really trick question, but I think it's kind of interesting. Why do you think the weight was bumped up to 2 here instead of 1?
To make the difference bigger.
Right, exactly. So to make a difference bigger, but I want you all to think of a specific case. Because remember, vertical line detectors, they detect vertical lines. And in the case that there is just nothing in the image, it's all a constant value, what happens? So imagine that we're applying this to an image of size 3 by 3. It's a 3 by 3 image. And say that the values are all constant. It's all 1s everywhere. What would you want your vertical line detector to output?
Something positive.
Okay, interesting. So why do you think a vertical line detector should output a positive value in this case?
Because it's easier to evaluate than negative numbers.
Ah, okay. Well, like as a computer, right? I don't think it matters. They like negative numbers equally as much as positive numbers. I mean, so is there a vertical line in this picture that I just drew?
Yeah.
Oh, there is. Oh, okay. Can you explain? I'm sorry. Maybe I'm being dumb. I mean, imagine that this is just a white canvas. Is there a vertical line in a white canvas?
Oh no.
Yeah, right. There's not a vertical line here. So if you apply a vertical line detector, you should ideally get an output of 0. This is just something that we define just for notational convenience, just for intuitive convenience. And that's actually why these are set as 2, because if you have all 1s everywhere or all some value x, it's just a constant value x, then the sum over all of this is actually just 6x minus 6x, which is 0. So it'll always be 0 if you have a constant value. So that's just like something that I wanted to bring up just to make sure that these concepts were going home. Like, you have these things, you're multiplying with them to find vertical lines. And in the cases where there's not a vertical line, you want it to be very low, you want it to be 0. But in this case, it doesn't really matter. Like, it's not imperative that this is a 0 when everything is a constant. You could set all of these to like -100. So then basically this would rescale your image, your output. Everything's going to be super dark except for a couple of vertical lines, which are faintly there. But in general, you know, the way that you design your filter, it's sort of up to you. But this is just one thing that you might want to think about, the boundary cases, so to say. All right. So
Yeah, so if, okay, so you have like a vertical and a horizontal line detectors, right? What if we have in the image, we have like a diagonal, the lines, the cross lines, either they're different directions, but the convolution gonna be the same value. We don't tell it's northeast to southwest or either northwest to southeast, the line in the image.
So if I'm understanding your question correctly, you have a vertical line detector, you will detect north-south lines. And if you have a horizontal line detector,
either northwest to southeast or northeast to southwest. You know, they're diagonal
okay,
lines,
so are you
right?
asking
but
how
different
that,
directions.
are you
right?
asking how would this
They're gonna give the
feature
same
look?
value. Yeah. No. They're gonna give the same value.
Wait, yeah, that's true. But it doesn't matter because then you're not looking for diagonal lines in this filter, right?
Okay. Yep.
Yeah.
Yeah, we need additional, yeah, right, to detect those.
Right, exactly. So the point is that if you don't have one of these features that you're looking for, you won't get a meaningful signal out. And that's sort of the point of learning these filters, which is the neural network will learn through gradient descent what features are important to be extracting so that they can adjust these filters to figure out what they are. So indeed, if you had any diagonal lines in your image, maybe these are not the best filters to be using. You might want something that looks like -1, -1, 2, 2, 2, -1, -1, -1. This would be a kernel. So that's like a possible solution to that. But hopefully this idea of a convolution makes sense, and now we can generalize it to neural networks.
Right.
All right. So this part's going to be pretty simple. We already know how convolutions work. You take a kernel, you slap it on an image, and you move it around. Or we haven't talked about the move around part. We'll get to that in a moment. But to convolve a patch of an image with a kernel, you just slap it on the kernel, and then you multiply all the values, and then you add them together. And we've seen through some of these examples that you can detect certain features in images. You can detect vertical lines, horizontal lines, any kinds of lines. You can even design a super large filter that actually, you know, looks for these kinds of edges or something like that, or whatever it may be. So some of the things that I wanted to bring up here is that when you have these kernels and you slap them on and then you move them across the entire image, we start to see promising patterns, which is these two images will get similar outputs. Because if you take the same filter here and then you move it around this image, and you take this filter and you move it around this image, at a certain point, you will get the same convolution between this cat thing and this cat thing. They'll produce the same answer if you use the same kernel. And this tells you that we're starting to make progress to our goal of translational invariance. That when you use the same set of feature detectors and you apply it across the entire image, you will extract the same features out if there are indeed the same features at any location in the image. And another thing to note here is that we're actually starting to reduce the complexity of our model. Remember that in our fully connected neural network layer, there was a new weight for literally every single neuron and every single neuron in the next layer. But you can see here, what we do is sort of this weight sharing thing, where this neuron connected to the next layer actually uses the same weight as this neuron connecting to the next layer, because you simply use the same filter again and again. So this actually reduces the number of parameters, and it can prevent your model from learning a hypothesis that is way too expressive. Or in other words, we can reduce overfitting by doing this, and also reduce computational cost. So we've talked about kernels. We've shown that they're useful in detecting certain edges. How do we put them together into a neural network? So there are a couple of considerations that I wanted to bring up before we talk about that. First of all is that your convolutional neural network can have filters of all different sizes. I've been using 3x3 because it's more tractable to talk about it this way, but you can use filters of size 1x3, 3x1, 100x100, a million by a million. It doesn't really matter, but there are certain standards that people usually adhere to. Like people really like using 5x5 filters, 3x3 filters, just because empirically people can see that they work well. But for different problems, this might be different, because essentially what the grid size defines is the number of pixels the kernel can see at once, right? And in some applications, if you want more global, if you want to accumulate more features more quickly, then you might want to use a larger kernel, maybe 9x9 or something like that. And of course, people like to use odd numbers so that there's a center pixel. It's just nice because of the way that the convolution works. All right, cool. There's also some detail here that I won't be going super far into, which is that you can, because if you notice, okay, actually this will be useful for talking about sliding. Okay, so imagine that we have a larger input now, right? This is now a 5x5 input, and we have a 3x3 kernel. So we can't just do this thing where we slap the kernel on the image, do the multiplication, and we're done. Because in fact, the input is larger than the kernel. So we have to do this thing where we slide it around now. We slide it around everywhere, and we get a bunch of different outputs. How is this done? Well, it's pretty simple. And there are a couple of parameters that control this, but let's just assume the simplest case for now. Basically, you take this kernel, this 3x3 thing, and you slap it on first at the top left. You start at the top left. You do the math, and if you do the math, I think this is exactly the example maybe that we did earlier, or probably not. You do the multiplication, you take the dot product between the kernel and the slice of the input, and you get -2 out. So what do you do next? Well, you just move over. You move over to the next one, to this slice, and then you take the dot product between the kernel and the input like that. So then, the relevant math would be just like -2 plus 6, and then this is all zeros, and then -1, -2. And so this should equal 1. Yeah. So then you would get a 1 here. And then you would keep going. You slide it over here, and you do it with this part. And then you keep going. You do it with this part. 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 And you keep going until you have reached the end of the image. So you do all of these convolutions. And as you can see, there are a lot of them. And you get eventually out this nine outputs from the 25 outputs. So what you might notice here is that after we do this sliding thing, because of the way that the convolution is computed, our thing gets smaller. Our output went from 5x5 to 3x3, which is a problem if you don't want the output to be reduced. So does anyone have any ideas maybe fix this? Maybe it's already on the slide here, so maybe I will just not say anything. And it's called padding. Okay, yeah, we'll just roll with this. It's called padding. The solution to this is, and it's quite simple. If you have an image, this is the image from before, I think, if you want to maintain the size, all you have to do is pad the sides with zeros. And then, of course, if you work out the math, then we will end up with a 5x5 image. If you want to pad it, it becomes 7x7. And then once you do the 7x7, you convolve it with a 3x3 kernel, you'll get back a 5x5 image again. So of course there are some edge effects, like you have no values over here, but that's okay, because then they don't influence the output of your kernel. You're still these are all zeros, so they don't influence the output, and it generally is okay. So if you want to keep the same size, then you will you'll want to use padding. In general, whether you use padding or not is sort of dependent on your application. Some applications fare better with padding, some don't. This is just something that you'll have to pick up on a case-by-case basis, and the more that you build models, the more that this will become obvious to you. So Benjamin asks, what happens if there is no center pixel? Well, this is a good question. I think it doesn't really matter, I would say. I think this is just a notational convenience that people like to use. So if in fact we were trying to do 2x2 convolutions, let's say with this image. So if instead our kernel was 2x2, so there's no center pixel, then this would give you, and let's say that our kernel, let's say that our kernel, let's just say it's K prime, and let's say that it's equal to the identity matrix, which is 0, 1, 1, 0. Let's just say that it's this, then we would get an output that looks like the following. So then we would have 3 plus 2, which is 5. Then we would slide it over here, and we would get 3 plus 2 equals 5. Then we would slide it over here. We get 1 plus 1 equals 2. And then we would get 2 plus 1 equals 3. So then you would get this as the output of your convolution. So it's not a big deal. Like, it still works, but it just has become convention that you want a center pixel there for some reason. I don't have a good answer to why. It might just be convention. There might be something that I'm missing. If I figure out that there's something that I missed, I will let you guys know at the next class. But this is a good question. All right. There's also another setting that we can customize with our convolutions. And basically what we're doing right now is we're building up to the fact that, we have this idea called a convolution. It can help us find features. Now let's discuss some of the parameters that can change the way that the convolution behaves. For example, we can add padding to make sure that the output is the same size as the input. And another thing that we're trying to do here now is maybe how the convolution works, whether we're skipping kernels or whether we're skipping things or we're not skipping things. And then finally, once we have all of these settings in place and we know that the kernels are there, then we'll put all of this together into a neural network, and we'll see that it does a great job learning these representations that can help us classify images or any data with spatial structure very nicely. So remember that in the previous slide, or pretty much for everything so far, I have been doing the convolution like this, and then afterwards I shift over to the immediately next pixel. What this is called, the difference between the original location and the ending location, is called a stride. And we don't necessarily have to take a stride of 1, because if we're doing this, we have a lot of overlap between the original convolution and this convolution. So one way that you might want to do things is after you do this, you can have a stride that does not equal 1. It does not equal 1. So maybe we can have a stride equal 2. So instead of going to this place, we would actually go to this place. Your stride would equal 2. So you would only have 1 sort of slice of overlap as opposed to 2. And this stride applies to both dimensions. So after you do this, you don't go to this area. You actually go to this area, and then you go here, and you do the convolution here, and then you do a convolution here. Does anyone want to just eyeball the size of the output for me? So what would the size of the output in this case be if we had a stride of 2 on this input? So 5 by 5, kernel, 3 by 3, stride 2. What is the size of the output? Yeah, exactly. This was in a DM, but it would give you a 2 by 2 matrix. That's great, because this one gives us a value x1, x2, x3, x4, and it would just give you a 2 by 2 matrix. So great. This changes the size of your image quite drastically. So when you do greater strides, you will reduce the size of your number of features that you're trying to come out with. by a pretty big margin. So this is basically it. You have all of these different things. You have the way that you can control the size of the output. You can add padding. You can increase or decrease your stride. And all of these things can change the way that your computer vision model looks for features in the image. Now, there's one other thing that we haven't talked about yet. This is the last thing that we need to talk about, which is depth. Remember that images are represented not using one number per pixel, but they're actually usually represented with 3 numbers per pixel. It's what we call RGB. I'm sure many of you are familiar with RGB. And basically, if you take an image, it's actually not just a 3x3 image. It's actually 3 3x3 images, and each of these images represents a different channel. So you actually have an image for the red color. So this basically tells you how much red is in the image. Then you have a green, which is how much green is in the image. And then you have B, which is how much blue is in the image. And then together, these 3 things, they actually combine to give you the original image. So in fact, you could represent your original image as a collection or an overlay of 3 channels. So you got the R channel, the B channel, the G channel. So you got these 3 channels. So this is something important to keep in mind, because your filter, if you have 3 channels, you can't really have just one filter. So you can. This is one way to do it. So one perhaps solution to this is you have just one kernel and you apply it to all of the different channels. But there is also a way of doing things, which is that your filter no longer is 3x3. It's actually 3x3x3. So it's like this little box where you have slices of filters down and under. It's like a little cube thingy. So you got a 3x3, and then you got 3 of them in a box. And what happens is, this is basically equivalent to saying we have a specific kernel for the R channel, a specific kernel for the G channel, and a specific kernel for the B channel. And they'll give you an output. Now, when you do the convolution, sometimes it's the convention to just say, take this kernel, convolve it with R, convolve it with G, convolve it with B, and then add all of the results together. Like literally just add everything together. Even though you have different kernels, you just do it all together. And so this gives you one channel back, and it just gives you one number back. It basically just gives you one number back. And this is the whole idea of depth, because it's a little bit more complicated in these computer vision scenarios. We don't just have a depth of 1, we have a depth of 3. If you do this, I don't even know what this stands for, but it's another color representation, CMYK. It has 4 channels. So you have varying depth, and sometimes this is something that you want to keep in mind. Now, depth is not only something that pertains to the input. You could have an input of, let's say like a 28 by 28 image, and its depth is 3, right? Because it's got RGB. And once you do a convolution, let's say that after you apply some kind of filter, the size gets reduced by half, down to 14 by 14. So this is what would happen if we applied one filter. You can actually apply multiple filters. So you got this huge cube thing of a filter. You can actually apply this 10 times, and you can get all kinds of different outputs from these from the 10 of these cube things. So then if you have 10, then your depth would become 10. And this is actually one of the ways that people that build neural networks get a lot more representation power and a lot more expressiveness into their models. So essentially what they do is, this is actually intuitively the way that you would construct you would basically incorporate multiple feature extractors. So for example, we could have one set of filters that looks for vertical lines, one set of features that looks for horizontal lines, one set of features that looks for triangular shapes, one set of features that looks for curved lines. And all of these are all different. So then you need different filters to represent them. So perhaps out of these 10 filters, you could have a bunch of different things: vertical, horizontal, curved, all of these kinds of detectors. You need many of these filters. You can't just have one, because remember, we said that one filter takes care of one feature at a time. So then you can increase your depth. So typically what happens in neural networks is that the dimensions, the dimensions of height and width get smaller and smaller. It might go down to 7 by 7 next time, but the depth gets larger and larger. Sometimes it gets to like 64 deep. What this is saying is that you took the input and you applied 64 sets of filters. So you could be looking for 64 different types of features for this image, and then they're all of size 7 by 7. So you have 49 by 64 features, which is a heck of a lot of features. So this is the whole idea of depth. And don't worry if some of this sounds, again, a little bit more, hand wavy, because we're going to go through a specific example of what a convolutional layer looks like, and it should all come together at that point. So finally, we have all of the components that we need to talk about the convolution layer. And just to make sure that everyone's on the same page, I will remind us what we have done so far. So first of all, we have shown that there are these things called kernels. These kernels help us find features, right? You convolve it with an image, and it can do a lot of cool things, right? It can find horizontal lines, it can find vertical lines, curved lines, triangular shapes, all kinds of different things. It can find features. But these kernels have some parameters. They're like these hyperparameters. We're back talking about hyperparameters, hyperparams. There are these hyperparameters that control their behavior, like stride, padding. We also talked about depth. All of these things control the behavior of these kernels, and they change the way that our neural network learns them. So then, combining all of these two different things, we want to finally, we're here at this stage where we can finally talk about a convolutional layer. So let's dive right in.
Okay.
We have this image. Let's
yeah.
say that it's 32 by,
Yeah.
sorry, is there a question?
Yeah, right. So what I see here, you find the features and you do the convolution. That will solve the translational invariance problem. Is it?
Sure.
Okay, what about the size invariance and rotational? Let's say you rotate it or different size. Will that still keep the same?
Yeah, so this is a good question. We'll get to this in a little bit. And in fact, convolutional neural networks are not always great at these two different things. There are some tricks that people implement to try to get this to work, but in a lot of cases, as we will explore in a moment when I pull up a demo, sometimes this is not great. Like you take a picture from a different angle, it still looks the same, but the neural network thinks it's something different. So there are these things called pooling that we will talk about that attempt to do this, but doesn't do a great job, but we'll still talk about it just for completeness.
Yeah, thank you.
All right, so you had a convolutional layer here. We have an image, right? This is a 32 by 32 image. I imagine if you looked at this image in real life, it would look very, very bad. Very pixelated, very jagged. You got, maybe it's a picture of a person, very pixelated, very blurry, but whatever, it's an image. And it's got 3 channels. So it's got 3 channels for R, G, and B. R, G, B channels. So in a more schematic looking view, this is what it looks like, right? You got 32 by 32. This is the dude's face or something. And you've got R, G, and B, the 3 channels. So this is our convolutional layer. And imagine that we have one 5 by 5 by 3 filter. And as we talked about, when we do the convolution, this is my way of putting it. I mean, this is Stanford's way of putting it. Slide over the image spatially, computing dot products. I like to say just slap it on the image and move it around. And you compute the dot products while you move it around. So basically, you just keep doing this again and again. They started out in the middle. It doesn't really matter. They can put it here and they move it around like this, like this, like this. They keep on taking the dot products. And each time you get out one neuron, right? You get out one output. So this gives you an activation map, right? This is an activation map. Remember we said that once you do the convolution, you get out one number for all 3 channels because we just add all the numbers up. And we get one number, but then we get 28 by 28 of them, which means that we reduce the size of the 32 by 32 image to 28 by 28 because we used a 5 by 5 by 3 filter. This is just how it works. If you tried doing it with 32 by 32 and you tried applying this 5 by 5 by 3, you would see that you would get 28 by 28 out. And of course, we only get one depth. But remember, this one filter might only be able to look for one feature. So we might want more filters. So then you can consider adding a second green filter. Then this would give you another sheet of 20 by 20 activation maps. And in fact, you can just keep doing this again and again. They've chosen to do this 6 times. It doesn't really matter what you choose. You can choose to do it like 20 times, 60 times. Just depends on what works for you. Yeah, then you can get out a block of 28 by 28 by 6. And intuitively, what you might think here is that each of these 6 slices is looking at a different feature, or maybe some composition of simple features. Each of these 6 is looking at something different. And basically, what happens in a convolutional layer is you just keep doing this a million times. Not a million times, but many, many times, maybe on the order of 10 if you're building a very simple network. The deeper networks can have 100, 200, 300 of these layers. You just keep on going, every time making the input a little bit smaller. See, 32 becomes 20, it becomes 24. And usually the convention is that you get deeper and deeper, which means that at every step you're extracting more and more abstract features. And eventually you get to the end. So they have omitted what happens at the very end, but basically at the very end, you might have a really small feature map, like 7 by 7 by 64. And what you would do is now you do the flattening. You do the flattening because all of these things, we've taken care of the translational invariance. We're going to explain how we try to take care of other types of invariances. But you get this 7 by 7 by 64, and this is exactly what we talked about at the beginning. You just flatten it. You flatten it into this huge 7 by 7 by 64, whatever this number is, 49 by 64. It's got all of these different values here, and you apply a fully connected layer. So this is what we call an ANN. This is your dense layers, whatever you want to call it. We're going to put it in here. And then you finally get an output. So this is in fact a convolutional neural network. We've built through the entire process of the CNN, modulo a couple of small details, which we'll get to at the end. So just to recap, you got these convolutions. They are very smart because we trained them using gradient descent. They have all these features. These features are coming out of these convolutions. We're getting features of the features. We're learning to figure out what the important parts of an image are to determine the correct classification. Keep doing this, keep doing this, keep doing this. Eventually we get a bunch of features at the end, and these are the very abstract features that sort of represent the image itself. And then we put it through a fully connected layer to do classification and get out the final result. So this is the convolutional neural network. Very, very simple.
Okay, can you explain why the depth is deeper and deeper? Or originally there was a 3, and it's in the second it's 6.
Yeah, so
10.
I talked about this a little bit earlier. You can think of these filters as looking for a specific feature, right? We talked about earlier, when you have one of these filters, it could look like this: -1, -1, 1, 1, 1, -1, -1. And this is what we call a vertical line detector. But the problem is, detector. Sorry, I can't spell detector. But the problem is that these images might have lots of different features that you're interested in. Maybe not just vertical lines, but perhaps horizontal lines, triangle shapes, curved lines, all of these different things. But you can't do that with your vertical line detector. You need different features.
Okay,
So
okay, I got you. That's a different, you add additional features, not
basically
the result of the convolution. The convolution gonna make it thinner, but you add additional features. Okay, gotcha.
Yeah. It's basically a huge dot product between this volume, and you get out one value, but then we do this a bunch of times for different features.
Right.
All right, so hopefully this all makes sense. Good questions. Can I get a thumbs up if we're all good on what we've covered so far? I know all of this is coming at us very, very quickly. Like, this is all stuff that you'd probably be learning in college, but you're learning now when you're very young. So this is very impressive. But okay, great that everyone's sort of following. I hope it's generally been understandable. Now we're going to get a little bit more concrete with everything, and let's look at what exactly these features are examining. I think this is an interesting question. So this is this diagram is credited to you, this person right here, a recent Turing winner, like Lecun. I don't know how to pronounce his name. He's French, but he was the one who invented convolutional neural networks, and he was able to visualize some of these things. So I think it's super cool what is happening in this image. This is a classifier that tries to classify a bunch of different objects. It's trained on a data set called ImageNet. It's got like a bunch of different classes. You know, it's got automobiles, planes, trains, fruits, animals. It's got a different bunch of classes where a neural network learns to differentiate between all of them. So you can think of these as the convolutional layers in this model. So maybe this is the convolutional layer. This is the first layer. This is the second layer. This is the third layer. Or maybe, you know, there are lots of different intermediate layers here. And maybe this is like the 20th layer. And this is maybe the 40th layer. Lots of intermediate layers here. So if we look at this image, there are lots of interesting things that are happening here. Like when you talk about the first convolutional neural network layer, it's got a bunch of low-level features. So as you can see, these are the filters that we're getting from the from training it through gradient descent. So we asked this computer, we're like, please minimize data, please minimize your error when you train on this data set, and let's see what the filters that come out are. You can see that we see a lot of line detectors. And these were things that humans were designing maybe like 50 years ago, but now computers are smart enough to design these line detectors themselves. So it's clearly looking for, you know, there are these diagonal line detectors, horizontal line detectors, vertical line detectors, and there are even these cool, weird looking color detector filters that perhaps compare different colors. It's looking for contrast. Maybe cars, they have a specific color, they're on specific backgrounds or whatever. So you can really see what the neural network is thinking. It's looking for these edges. And then the interesting trend here is that the further that you go, the deeper that you go in the model, the more strange and abstract these features become. Some of these might be interpretable to you. Like, for example, this is looking for circles, which might correspond to the wheels in a vehicle, which is quite cool. But you can see that at the beginning, you just had a bunch of lines, you know, that are very, very, very basic. But the further that you go, the model is sort of composing all of these features that you get out and looking for higher level features, these weird looking, strange looking things that it's trying to look for. These circles maybe correspond to wheels or other round objects. But the further that you go, the more and more abstract these features become. That's sort of what I'm trying to get at. And it's sort of cool just to look at these features and be like, it really is looking for lines like we talked about, like humans imagined 50 years ago, and now computers are smart enough to design these line detectors. So quite fascinating here. This is just to give you some intuition for what's happening. And just again, to remind you all, the operation that's happening is you take this image, you convolve it with every single one of these features. So then you would get out a depth of 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6. 5 by 6 is 30. You get out a depth of 30 at this first layer. And then you just keep going until you have the fully connected layer, or the dense layer, the ANN layer, whatever you want to call it at the very end, where you can classify and figure out, hey, this is a car.
Okay,
So,
question about
yeah.
those features. Are there any ranking about these features? Because the features can be unlimited. I mean, you can put as many as you want, right? However, can we measure which one are very strong? Let's say like any animals, we have like a 2 eyes, right? A 1 nose. That would be very strong. That's an indication that we're kind of like a animal, let's say.
Yeah, so I think in general, like, you can, maybe one way to see this is you just look at the activations from the filters and you see which ones are super high, and that's what the neural network will focus on. Obviously, if you have a horizontal line in an image and then you convolve it with a vertical line detector, it won't activate very much, so the neural network won't pay attention to it. So this is one way to do it. You look at the feature maps after the convolution, and you can be like, this feature map activates very highly, so this will be considered strongly in the future, or etc. that's one way that you can do it.
Okay, good.
All right. And of course, this is some more interesting stuff. I won't go into this in huge detail here, but these are some more examples of activation maps that come out. And for some reason, Stanford's professors decided to put the definition of convolution here. I think that this is not exactly the formulation that is used because this is flipped. The convolution that we talk about in convolutional neural networks is actually the flip of the real convolution, but that's okay. But in case you're curious, this is what the formulation looks like. Your F might be the image and your G might be the kernel. It doesn't actually matter because convolution is associative, is commutative, which means that F convolved with G is equal to G convolved with F. So it doesn't matter what it is, but you can convolve your image with your kernel. This is the math that we were talking about. You might recognize this as a multiplication. So we're basically just summing all the dot products. The sum of the dot products you might recognize as the dot product. So in case you were curious, this is where the math comes from. This is the more formal way of writing, to take your filter, slap it on the image and move it around and smear it around. This is the more mathy way of saying that. So again, here are some more visualizations. You got a car here. You have the convolution produces all of this stuff, and you go through the huge convolutional neural network. And at the very, very end, you get a fully connected neural network that takes in all of these features at the very end and is like, this looks like a car. And then it'll output a super high probability on the car. And then maybe it's close to a truck because cars share lots of features with trucks, airplanes. These are all sort of like transportation methods. So as you can see, convolutional neural networks can be very effective at this kind of task. All right, so we've talked about a lot, right? We have the input. You get convolutions that iteratively make this thing smaller and deeper, where we look for features, and then eventually at the very end we flatten everything and put it into a fully connected layer. So there's only one part of this puzzle that we're missing, which is this thing called subsampling. And it's a method, it's a non-parametric method, which means that there are no weights to learn here, but it's just a method of simplifying our problem because images can be super big. And when you run these models on super big images, they can be very slow. And a lot of the times you do redundant operations like we were talking about. If you do convolutions with a stride of 1, you might be applying the same weight to the same pixels a bunch of times. So sometimes our desire is to make the problem a little bit simpler. And the way that we do that is called subsampling. And so subsampling actually takes a form called pooling. Pooling. It's an interesting name. It's called pooling. So the idea is to reduce the image size by matching a patch of pixels to a single value. And a lot of you, if you think about, I mean, I don't know if you've thought about this before, but if you ever thought about compressing images, for example, if you have a huge image, right, and you don't have a lot of memory on your computer, how would you make this image, how would you compress it, right? How would you make it look not horrible? You can still tell it's the same thing, but you use less space to represent the image. There are lots of cool methods that I won't be talking about today. How JPEG does it using Fourier methods. We won't talk about that. But one really dumb idea is if you have an image, let's say it's a huge image, you could basically just take a patch of this image, average all of the pixels, and make it 1 pixel in the output image. And then you would do that for this next pixel patch. You make this the next pixel in the output image. So eventually you get this smaller image out, and it still looks generally the same because you're just averaging a bunch of nearby pixels. And we established before that there is spatial locality to images. Pixels that are close to each other generally are sort of close to each other anyways. And then we just we get a smaller image out. This is exactly what pooling does. It just takes the image and it makes it a little bit smaller. And this is, you can think of this as a form of compression. And I'll talk about how this relates to rotational invariance in a moment. But let's talk about how exactly pooling works. There's a very simple example of this. So if you have a 4x4 image and you want to reduce its size, what we do, there are lots of different types of max pooling. This is basically the operation that you use to compress a certain patch. But max pooling, as the name suggests, is just to take the maximum. So in this light blue patch, you would take the maximum, which is 8. And in this yellow patch, you would take the 5, the 1, the 4, and this is what you would get out. So you get something that looks vaguely sort of like the original image, not really, but it's a more compressed representation here. But what's the power in this? You might be asking, well, why do we do this? It seems like a very arbitrary operation. You seem to throw away a lot of information. Well, first of all, we established before that there's this thing called spatial locality in images where pixels are all usually pretty close to each other. So we can afford to maybe throw out 3/4 of the pixels and be like, yeah, we could just average them all into one of them. That's one perhaps reason that this is not that bad. And the second reason is that max pool is actually sort of rotationally invariant. I'll explain what this means in a moment. But let's just look at this this 2x2 patch here. So you got 2, 1, negative 3, 8. Apologies for the awful writing. 2, 1, negative 3, 8. And imagine that we took this image and we rotated it, or maybe we transposed it. So it becomes 2, negative 3, 1, 8. When you apply max pool to this image, and when you apply max pool to this image, do you get the same thing? Yeah, right, exactly. You get the same thing. So what this tells you is that, in fact, max pooling and all these pooling methods are invariant to any type of permutation of these pixels. Rotation is just one such permutation. You can even just like switch the pixels in an arbitrary order, like 8, 2, negative 3, 1, or 8, negative 3, 1, 2. All of these things will yield the same thing. And the whole idea here is that if you do this, you will have some semblance of rotational invariance, or actually an even stronger thing called permutation invariance, but usually you don't permute your pixels randomly. That doesn't really make sense. So if in the case that this patch represented a cat, or the features of a cat, even if the cat was sideways, you would get the same thing out when you do max pool. So this is sort of the way that people try to incorporate rotational invariance. Now, in practice, does this always work well? Not really, because originally, if you have a cat and you convolve it with a filter, it'll give you something, but the filter doesn't rotate when the cat rotates. So you're gonna have to learn some pretty robust filters if you want these two to output the same thing. So in general, this is like a good idea, right? The fact that you can summarize these pixels while not really caring about the rotational location of all the pixels, but in practice, it doesn't always work too well. And I'll show an example of this in a moment when if you rotate an image, the neural network will become confused. If in any case, and we'll talk about this maybe in a future lesson, there's this thing called, there are these things that you can do called data augmentations, which is basically in your training data, you might only have upright cats, but what if you took the cat and you rotated it and you trained your model on that cat, both the rotated and the original cat? Well, then maybe you'd hope that your gradient descent algorithm would find a filter that reacts to the different features both just as well. So this is sort of the pipe dream. Does it always work? No, but generally when you do data augmentation, your models do become much more robust. So it's definitely something you should do when you design your own models. The reason that I won't be talking about this in detail is that the emphasis of this course is not to really hit home every single thing that you need to do to design your own models, because in most of the applications in this class, you will not be designing the model. Somebody else will have designed it for you and you'll simply be using it. But it's very interesting to observe the behavior of these models and say, when they do fail, you can sort of understand why they're failing. For example, if you have a classifier, like we'll show you a classifier in a moment here. If you have a classifier where you rotate the phone and it gets a rotated image and it doesn't work anymore, you can attribute this problem to this issue of rotational invariance being very difficult to achieve. So they're just like cool insights here and there that you can gain from understanding how these models work. Of course, there's also a different way that you can do this, average pooling, which is you just take the average of all these pixels. It's not hard to see that this also fits under the permutation invariance. It doesn't really matter what order in which you sum the numbers and you divide them, it's always going to be the same thing. So these are two very common ways of doing it. I think max pool is a little bit more common for reasons that I cannot understand. So yeah, that's sort of just the general thing in machine learning. You just do what other people do, and it's sort of like an alchemy at this moment because people don't really understand how deep learning works. It just somehow works. There's a lot of theoretical work that shows that it shouldn't work, but it happens to work super, super well. So just keep that in mind when you build these machine learning models. They're not gods. They don't know everything. They're simply these big bag of numbers that we trained using some algorithm that happened to work sort of well for some tasks. But they are still very, very cool, and we'll get into a lot of the amazing applications of them in a moment. All right, so this is the last slide of the presentation. We have sort of conquered this beast, right? We started out with the input. We have convolutions that get out features. We have subsampling that simplifies the problem for us while adding a little bit of rotational invariance. And then you take this block and you repeat it like 100 times. And then you get out these features where after you flatten them, you put it into a fully connected layer, and then you get an output. And ultimately, that is all there is to convolutional neural networks. Any final questions before we start getting into the lab?
So in practice, how many layers in the full connection layers, or is that one layer or layers? Could be layers. Right?
Yeah, this is a good question. I mean, it generally varies. You just sort of try things until they work well. You can have just one layer if it's a simple problem, but usually maybe 2 or 3 is a suitable number. It sort of depends.
Yeah.
All right, so I'm going to pull something up. Just give me one moment. And in the meantime, you all can open up MIT App Inventor and we will get started with that. Oh, also, would you mind, Dad, sharing the news about the Android device? Just make sure that everyone has one because today's the first day that we need that while I pull this up. The Android device. Also, you're muted. You're still muted. All right. Okay. So apparently my dad's computer is not working well. So the idea here is that we're going to start needing Android devices for all of the things going forward because MIT App Inventor's extensions that use artificial intelligence do not support iPhones just yet. So we sent out an email about this a couple days ago, I think. If you don't have one, then you can sort of just look on. You can just build out the app along with us, but you just won't be able to test it. So once you find an Android device that works, you'll be able to test it. Does anyone not have one? Can you drop a message in the chat? If you don't have an Android device, let me know. So I'm not getting any messages. I'm going to assume that this means that everyone does have it. That's really cool. But that's great. All right, give me 1 second while I try to find this thing. Ah, there we go. Okay, is this screen share working for everyone? Can you see what I'm doing here? Okay, cool. This is an example of, this is a visualization. I will throw it in the chat if anyone is interested in seeing this. This is a visualization of a convolutional neural network that's working on the MNIST dataset. The MNIST dataset is something that it's the handwritten digit dataset where you can write in maybe a thing here, and it's going to guess what the character is. So in this case, you can see that the model did a pretty poor job because it thinks that the actual number is 8 and its second guess is 5, even though I wrote a 4. So this just tells you, like right off the bat, convolutional neural networks are not perfect. But if I try to draw it a little bit more carefully, you can see that it now gets the correct answer. It gets a 4. So just feel free to play with this. I dropped the link in the chat. You might notice that maybe when I write a 2, its first guess is 2. It's great. Everything is well. Let's try to test, maybe the invariance of this thing. Wait, hold on. I'm going to try to draw 2 here. That's like sideways. So as you can see, this thing clearly was not trained on rotated images, because you can see that the first guess is a 7 instead of a 2. The second guess is a 3. It's way off. But if we do a 3, it gets it correct. If I put a 3 in the little corner, it also starts to get confused. So the first guess was a 1 instead of a 3. If I put a 3 in this corner, another first guess is 1. If I put an 8 up here, its first guess is 5. But only when I hit it in the middle is its first guess 8. So you can see that, perhaps this isn't the most intelligent convolutional neural network. This one looks really, really shallow. It's only got 2 layers. So it's not going to be the most robust thing in the world. And they did this purely, I believe, because of their visualization requirements. But you can see that convolutional neural networks, while they are super cool, sometimes they don't work. And when you're building your own models, you got to keep this in mind. And yeah, so you can see, like, works reasonably well. It can guess a 7, but once you put a thing through it, it still guesses 7. We can put a 9, works, etc., etc. So this is just something that I wanted to bring up. But I think now we can go into MIT App Inventor, and let's start with the lab. So today's lab is going to be in 2 parts. I'm going to be screen sharing for most of it, I think. The first part is we're just going to import a convolutional neural network into MIT App Inventor, and we're going to see what it does. It's going to be pre-trained for us already. It's basically trained on ImageNet or something like that, and it'll work out of the box. But the cool thing is that next time we'll be able to use or the next part of the lab is to use an online interface to create our own models and then import them into MIT App Inventor, and then you can use it for whatever purpose you want. And so this is cool because it allows you to collect your own training data. Say that you wanted to use a model to determine whether or not you're holding up a palm or a fist. You could basically train the model on a bunch of different sort of like configurations of your hand, and then a bunch of different configurations of your palm, and then the model would learn the difference between the two, and it would be able to predict it on your cell phone whenever you do this on your cell phone. So,
yeah, I think that one, the cool stuff for that one is to tell the twins. It's really hard to tell the twins who is who, right? So yeah, if we can play the images with of the twins, the pictures of twins, we can tell which one is which. That would be cool.
Yeah, okay. I don't know what this means yet, but I guess we'll find out. Okay, so I just dropped a link in the chat. Please open it. This will be the template file for what we're going to be using, because this is sort of like an official document from MIT App Inventor that tells us how we're supposed to use this thing. So go ahead and open it, and then drop an OK in the chat once you have it open, because this is going to be the way that we are doing everything. So I'm going to go ahead and connect my phone to AirDroid so that I can show you all what's happening, and we can get started. All right, so I've got 2 people who are okay. Let me know when just let me know as things start to work. Okay, great. I'll give people, it seems like 4 people have it working now. I will give people like 30 more seconds. But as you can see on my display, this is what it should show. Like you can see my whole computer setup here. This is the camera, and it shouldn't work yet because we need to build whatever it's doing. So it shouldn't work quite yet, but you should be able to see this like camera little thing that's displaying everything. Okay, if you don't have this up quite yet, don't worry, because I'll just be talking. Just continue working on this if you don't have it to this stage yet, and it'll be okay. So this is the thing, and MIT App Inventor's got this tutorial thing where we have like instructions to connect your app. This is not so interesting. You should all have done this already. So let's just dive into the tutorial. It'll tell us what we should do to make this thing be able to run. So they've already built out the interface for us, so we don't really have to worry about the components of the app. Of course, we already know what the blocks editor is. The toggling the camera's direction, I think, is not so interesting. I think we will just skip it for now. Because what we're actually really interested in is the look extension. So the reason that I had you all import this specific project is that if you look at the extensions, the look extension has already been imported for us. That's the key here. So what this thing is telling us to do is we need to be able to wait for the look extension to load, and then have it load up, and then we'll be able to click classify. So to do this, let's go to our blocks, and it's telling us that we should go to our extension and be like, okay, when the classifier is ready, what should we do? Well, if we look at the interface here, it says waiting. Perhaps one reasonable thing to do would be to make it so that it says that it's ready, so that we know. So we can go to our status label, and we can say set status label.text to, let's say something like classifier ready. Classifier ready. All right. And to make this work, maybe we should refresh the companion screen. And here you go. It says classifier ready, so that we know that everything is working just fine, and it's gonna be able to do classifications. So the next thing that we need to do, notice that our classify button at the very bottom is disabled. We're not able to use it actually. So we also have to make sure that we can enable the classifier button, which should be pretty easy. There should be something here to set the enabled. I think it was up here. Yeah, we can set the enabled to whatever it should be. I think it's just true, the Boolean value. So let's go ahead and refresh the companion screen again and see here. Okay, cool. So when the classifier is ready, we can now click this classify button, which doesn't actually do anything yet. So naturally, the next thing that we need to do is to go to our classify button and add the event handler for when it's clicked. And what has happened, what we want to happen when it's clicked, we need to look at our instructions for, right? Because it's going to tell us specifically how to use the look extension. And so it's saying that whenever we want to do this, we want to drag the block call look extension.classify video data into the clicker. So it's just going to do classify video data, and it should be doing something. But actually, the fact that this doesn't return anything should set off alarm bells in your head, because there's no telling it where to deposit the outputs. So you actually probably have to design some code to handle it whenever you get the extension result back. And in fact, there's like this nice method called got classification. So you get a classification, you get a result. I think the most natural thing to do is to set it to the status label. So we can set it to, perhaps we can join it. We can join label, label, and we can get the result and put it in here. And let's just see what happens. So I'm going to, let's just hard reset the emulator. Well, okay, maybe not. Let's just reset connection. So this thing has died. Let's try to reopen it. I will scan the QR code. Okay, cool. So it's got a classifier ready, and we should have been able to implement all of the code to make this work. So I'm gonna hit classify, and okay. So it's given us a bunch of things, right? It's given us a display, 0.62. Basically, it is 62% confident that what it's looking at is a computer display, which is in fact correct. Very nice, good job for the computer. It got it right. And so we can try like a bunch of different things. You know, we can take this water bottle, we can click classify. It thinks it's wine, beer, so it's not quite right. The cup is a little bit closer, but it's only 2%. But you can see that maybe if I change the direction, maybe we can get a better classification. Or maybe we need a different background, like perhaps this. So it has water bottle here at 0.8, so 0.08, which is not awful, not bad. I guess like we can try a bunch of other different things like this. A pill bottle, not quite, not quite right. This microphone might be a little bit hard for it to identify. It thinks it's wine again, stove, or let's see, does it know that this is a laptop? Oh, okay, so great. It knows that it's a display, a laptop keyboard, so that's good. Obviously, this one display worked. This display also worked. So what about this? I don't know, a lampshade. Okay, so it's also correct. So as you can see, I hope you're also playing with this at home. It like generally works pretty well. There are some cases in which it's confused, but that's probably because we don't have the specific classification in the model. You know, maybe if you showed something super obscure, it won't know what it is. I guess one more thing we can try are glasses. Sunglasses, okay. So they are glasses, but they're not quite sunglasses, but that's okay. So quite close. As you can see, works pretty well, not bad. And I think this is pretty much the extent that we'll be doing with the look extension. So it's pretty cool. If you imagine how you as a programmer would write such a piece of code to take in just a bunch of arbitrary pixels that you get from a camera and be able to identify what's in them, it's quite a complicated problem. And I think it's quite incredible that we have this code that can string together a bunch of random numbers, or not random, but seemingly arbitrary numbers to get it so that when you point it at something, it actually knows what it is. So very cool. All right, so this was the first part of the lab. The second part of the lab is going to concern how we can build our own models, because the look extension right now is only supporting whatever extension, whatever model that was already pre-built into the program. So now we're going to look at training our own models, and this will probably give us some insight into how exactly we should be designing our models in the first place. So give me one moment as I pull the second part up. All right, so this is an interface from MIT App Inventor that allows you to to capture basically training examples for your data. So remember, of course, whenever we train these models, we need a big data set so that we can put this data into our model, we can see how bad it is, and we can penalize it for being bad, and then find the optimal weights that to optimize the model. So this is just like a quick concept check. What are the weights that we have in our convolutional neural network? Does anyone want to suggest an answer to this? The weights that we are training, what are they? Any takers? Okay, so Benjamin's asking an administrative question. How do you download the app on the Kindle Fire? Just Google it. The instructions are probably on Google. I don't want to hold up the class, but it should be pretty simple to find out. If you're still having trouble after class, I can stay on for a couple more minutes and we can figure it out. But yeah. So the answer to the question that I asked earlier was that the kernel, or rather the weights of the kernel, are the things that we are training in a convolutional neural network, in addition to, of course, the weights in the fully connected layer at the very end. And this is of central importance. So if you didn't know this, make sure to review everything that we talked about earlier, because it's basically what we've been talking about this whole time, which is you have some features that you want to extract. How do you extract them? You need a kernel. How is this kernel designed? Well, the computer learns the weights through gradient descent. So this is a very important thing that you need to understand. All right, so we're on this training page. You can capture a bunch of things. And there's no labels here. Maybe we can add a label. So if we were trying to do whatever we were talking about earlier, which was whether you're doing a sort of like hand thing or perhaps a fist, we can do palm, and we can do fist, and we can capture for fist first. I can just hold down capture, a bunch of examples of my fist. I might rotate it a bunch of times and just keep clicking. You can see that I've clicked through like 50 examples, and maybe that's good enough for now. So then let's capture for palm. Our palm can capture for palm, all different types of sizes and stuff. We might want to rotate it. Or something like this. Okay, so this is fine. And then what happens when we click train? So it's going to load this thing called MobileNet. It's going to build the model, and it's going to perform training. It might take a moment. So it's training, the model loss is decreasing. Oh, it's almost 0. So then now we have a model, right? We have a model, and we can try capturing, and it's going to say this is a fist with confidence almost 100%, which is really nice. And then there's palm with confidence of nothing. So we can keep doing this. Like right now it knows that it's a palm. Right now it doesn't really know that it's a palm. Now it knows it's a fist. And the reason for this might be because I didn't really do any of these FAR classifications using a palm. So like obviously you can see that it works like fairly well. You have a palm here, you have a fist, so it's working. In MIT App Inventor, if you want to import this, basically you would go to export model, and what happens is you get an MDL format thing. No clue what this is, but you would download it. And let's take a look at how we might import this into MIT App Better. I'm actually not completely sure. We'll figure it out together. So let's see. All right, so there's this thing that we can load into MIT App Better. I'll send the link in a moment if we can all figure it out. So it's going to be loading for a moment, but just to give you a preview of what is to come, this idea of building your own model and building an interface to help support your model is going to be super important, because in a lot of applications, you have these models that people have made, and all you need to do basically is to assemble them together in a nice interface. And this is basically what you would do for a hackathon or a science fair project. So your homework will be to use this personal image classifying thing. I'll put the link on the master sheet after this class. But you will take this thing from MIT App Inventor. You will build your own model. Like, you don't have to have just 2 classifications. You can have a bunch of them, maybe like 5, 10 classes. You'll build your own model. You'll download the model, and you will integrate it with MIT App Inventor such that it does something cool. You have a lot of creative liberty with this assignment. Like, you can do whatever you want, but just make it so that perhaps it's useful. Maybe it's a problem that you've been trying to attack, something that you've noticed that's difficult. You know, just whatever it may be, just try something new, and it should be fun. So let's try to figure out how to get this personal image classifier thing to work. Add your model. Click on the personal image classifier, then click on model and choose upload classifier. Okay, so you can go to personal image classifier, you can go to model, and you can upload it. Okay, great. So we figured it out. This is how you do it. If you were following earlier from this code that we were doing with the look extension, where, you know, we had this thing. So what you need to do if you want to use a custom model is you go down here to look extension, and you go, oh, actually there's no upload here. Interesting. So these are actually different extensions. So you would need the personal image classifier extension. And basically, if you had the personal image classifier extension, you'd be able to upload your model right here, and you could be able to call it using the personal image classifier API. So I will send this, I'll post this right now in the chat. I'll also put this in the master document. But your assignment will basically be, again, like I said, to create your own convolutional neural network that is able to do whatever interesting thing you want it to do. You might want it to classify fruits. You might want it to differentiate between your dog and your cat. You might even want to make your own personal security system. So you're like, you're trying to classify whether the person in the image is you or perhaps your parents, and perhaps you can unlock a secret vault of files or whatever if it's you. You can basically make face unlock. So there's a lot of cool stuff that you can do with this. And feel free to impress us. I think it's going to be pretty interesting to see what everyone comes up with. But yeah, I'll post more detailed instructions in the master document later. This pretty much wraps it up for this class. I hope it was interesting to learn about how all these different applications of artificial intelligence all rely on convolutional neural networks. If you think about self-driving cars, they need to be able to detect people and images. They need to be able to do a bunch of stuff, navigate their environment, sense their environment, perceive their environment. It's all done with convolutional neural networks. If you think about looking at an MRI or looking at a CT scan and trying to diagnose somebody with some condition, this also heavily relies on convolutional neural networks, and et cetera, and et cetera. So there are so many different applications that rely on this very simple idea of extracting features and having a computer learn all of these features. So it's a very powerful idea that you now have under your belt, and you are now prepared to build a really cool application, whatever it may be, for homework. So any final questions before we end for today? Okay, I will take this as a no. So thanks everyone so much for coming. We will see you tomorrow for our next lesson. Feel free to reach out if you have any questions. See y'all.